looks excellent.
These are the
Good
science,
stuff.
huh?
Yes, lots of good science.
This is one of our plankton nets. We're sending it down to 800 meters, which is the deepest tow that we do. And then the boat goes ahead and we catch everything in the net that happens to get in the way of the net. It's a very fine net. It's about 300 thousandths of a millimeter. So anything smaller than that will pass straight through. And it gives us an idea of the biomass in the water. It's pretty much a plankton tow in a nutshell.
It's just to continue to get more information on what types of animals and plants are at different depths at what time of year with different light and different currents. And
it's pretty lifeless, really, because it's summer and it's less cold, and that means that there's less nutrients out so that the plants can't grow.
In March it would be like a lot rougher, and that would stir up the water and bring up colder waters from deeper and bring up nutrients.
it's called bloom season because the phytoplankton bloom and the zooplankton come along too to eat them.
Well, CTD stands for conductivity, which is a measure of salinity, temperature, and depth. So basically we're looking for correlations and relationships between depth and temperature and salinity. And also we're doing some measurements of presence of chlorine and fluorine as well. So those are pretty cool.
This is CTD. If you all look up under here, that's actually the CTD, okay? So that big white casing with lots of plugs going in, that's actually the little computer, that's the CTD. These on here are your fluorometers, which are telling you your chlorophyll, and you've also got oxygen sensors as well. Now all of these are called Niskin bottles, and we have 24 12-liter Niskin bottles. So we send this down to 2,600 meters, and we'll say, close bottle number 24. And it will close it, and it'll close from the top and the bottom, so it's got that water in it. So we pump these all at different depths, and then that gives us our profile.
The CTD stuff, I didn't think it was going to be that big a piece of equipment. I mean, it was pretty huge. It's like, you said a cylinder, I was like, one single cylinder, they shoot it down, it comes back up, it's over. It's like a big, huge cylinder with a lot of mini cylinders all around it, and they suck up information. It's pretty awesome.
Yeah.
Well, then some of it should still hit.
It looks like it's kind of hinged.
No!
Today we're at Hydro Station S, which is actually the longest time series. It was started in 1954 by Henry Stommel. So what a time series is it's going to the exact same spot over time. We go out 1 week every month. The BATS lab they've gone out. We go out in the worst storms and we always get the data. Hydro Station S is 15 nautical miles southeast of the island. There's a few reasons why it was chosen. It is not affected by the island currents. It's far enough away. The one amazing thing and the one great thing about Bermuda and why it's used for a lot of the studies is because the minute you get away from Bermuda, you're in blue water, you're in deep water. If you were off the coast of Massachusetts, you'd have to go out for a day before you hit deep water. Secondly, the Sargasso Sea is an amazing place to study. It's kind of like a desert. It's the reason why Bermuda has such blue waters. It's because there's very little life per se. So you've got this area where you've got pure ocean water that you can study, and it's an hour and a half from the island.
They've been doing it for about 50 years, so basically it's a source of information which no one else really has.
And when it comes to climate change and all that type of thing, you can say to somebody, yeah, temperatures are increasing or sea levels are rising, and we have the proof because we've been doing it for 50 years.
this is live data, so 300 meters on the way up. So on our CTD, we also have oxygen sensors, so dissolved oxygen, and a fluorometer. The fluorometer is a measure of the chlorophyll in the water. So as I say, the first one is the fluorometer. And as you can see, somewhere near the surface, in this case probably about 100 meters from the surface, we actually have a peak. This is known as the deep chlorophyll max. And basically what this is where there is the highest concentration of plants floating in the water. So this is where the optimum amount of nutrients and the optimum amount of light are. The blue line is our dissolved oxygen line. And if you actually look, there is a peak in the oxygen line that corresponds pretty much exactly with the peak in the chlorophyll line. Chlorophyll is plant life. Plants are photosynthesizing. Photosynthesis creates oxygen. Hence, the peak in the oxygen profile.
Manganese chloride 3 molar and sodium hydroxide, sodium iodide. And what it's done is it's created a precipitate. So it's taken the dissolved oxygen and it's basically poisoned it so that it precipitates. When we release it with sulfuric acid, then we can measure it again. So I get to get all my grievances out.
The main difference between what we did yesterday and what we're kind of doing today is yesterday's a lot more hands-on. Like you're in there, you're in the water, you're doing things right there. You can touch it, you can do it. Whereas here, it's like a lot more equipment. And I guess that's just because of the depths and whatnot. But I don't know, marine biology seems a lot more hands-on, and oceanography seems a lot more with the use of equipment. So it's pretty different and dependent on technology.
Well, for me, oceanography is more of the bare science of things. It's more to do with measurements rather than looking at fish and corals. It's just like temperature, salinity. So I guess it's more of a chemistry oriented field, and I find it quite interesting.
You can see the ocean as a giant, I guess, puzzle that works all together, and if you remove some of the pieces, the other ones can't fit. So if the deep oceans have big changes going on and heating and rising of currents, the places like the coral reef are not going to survive because they need that stable environment that they're used to. Like the corals are very sensitive, just a little tiny 1 degree temperature changes. So if there's changes going on in the deep ocean, it will definitely affect other parts of the world, like the reefs and the coasts and everything like that.
Well, thanks, Alessandro, and you're quite right. All the systems, as we study them by themselves, the coral, the seagrass, the deep ocean, they're all interconnected. And what we do on land and in our coast can affect the deep ocean the same way the deep ocean can affect the coast. As well as studying these things, sometimes we have to give back and actually take care of them. And we decided that part of what we could do would be to take care of a section of coastline that's really needs some restoration work. That's out at Cooper's Island. So we decided to try to protect some of the coastline by planting some of the native species and getting rid of some of the invasives, the casuarinas, which can rip up the coastline with their roots. Cooper's Island is sort of a work in progress, and this is one of the first years that students have been allowed to come to Cooper's Island to try and do some restoration work. So the guys here today have kayaked some cedar and palmetto, some endemic trees, to the island, and what we're doing is just trying to clear out some of the wedelia, which is spreading out everywhere, put some of the endemics in the ground, and it's kind of exciting for them. They're right at ground zero. We've told them this is a 50 to 100 year project. They're in the first year of it. And what they'll do is we'll use our GPS to mark wherever they put their trees, and then hopefully in future years come back and see how they're growing and mark their progress and so on. So
1, 2, look at that. I ball. Ball. One strong ball. got it.
Well, we're just getting rid of the invasive plants and planting our native plants.
The cedar, the olive, and the palmetto are all endemic to Bermuda, meaning they are found nowhere else. And if these plants wipe them out, and we don't do anything about them, then they will be gone forever.
Right now, I'm picking up the Bermuda palmetto and the Bermuda cedar tree. We're planting our cedar tree.
Okay, Malachi, can you grab the palmetto and put it in the hole and just see if it fits? Okay, so you're supposed to have the hole twice the size of the pot. So do you think we're there?
Yeah.
Pretty good? And what you can do is just put your hand around the base, turn it upside down, give it a little pat, and hold it. Got it?
Ooh.
Watch it, watch it.
Okay. So what you want to do is leave it in a little basin so that any rain that falls in will trickle down. And now Glenn's just getting our GPS from the boat as well, so then we need to mark where it is and we'll estimate the height.
Yeah, it's a lot of fun.
Dirty work.
It's hard work.
They get a lot out of it, but it's they've estimated 30,000 trees will need to go in the ground in order to turn this into a replica of a native forest. Long way to go, but I think you know, they're learning a lot and having a great time doing it. So.